Welcome, everyone, and everyone on video conferencing. Thanks for coming. And for those joining us on YouTube, you can, or you should, hit the continuous loop button. It should be down there on your screen somewhere. It'll be like techno, but it'll make you smarter. It is my privilege to bring to Google today 3 guys who have been working on Coreboot ever since it was known as LinuxBIOS several years ago. And they're all good friends and mentors of mine. And so we're going to talk about pretty much everything, starting with motivation, a little bit of history. We're going to move on to some details. We're going to talk about testing, and it's all going to be sprinkled with demos. And so without further ado, Mr. Ron Minnick, Stefan Reinauer, and Peter Stuga.
Thanks. Thank you. This is working. It's good to be here. We're going to give you a real variety of things, and I'm going to start with sort of the origins and then the high-performance computing perspective, which initially drove the development. We were lucky enough to go to Pete's this morning, and the first thing that happened is all the Windows-based cache registers crashed. And we're standing there, and they said, please wait a second while they reboot. And we all stood there thinking, yes, if only, knowing that the BIOS would wait about 3 minutes while it said, I think there might be hardware I can find. So, you know. So where did this thing start? It started in 1999. I'd been building clusters for about 8 years at that point. And I was pretty sick of watching the various BIOSes do things wrong, especially after power failures. So the goal was that Linux would boot out of Flash, and we would kill the PC BIOS, because everybody hates the PC BIOS that's ever had anything to do with it. And at the time, and even back then, actually EFI existed. So if you kind of looked at it, your choice, what choices you had, there was the nascent EFI, which was a proprietary closed operating system. It was extensible. It was written in C, but the driver thing is always the killer with this sort of stuff. So we looked at open firmware, and the answer to the other 3 questions is, well, fourth, and fourth, and I don't want to write drivers in fourth. So that was kind of flat out. And then, of course, the ancient and honorable PC BIOS, and to this day, the extension language for that is 8086 binaries. Which is exciting, and I don't want to do that. So finally, we thought, well, let's put Linux into Flash and save ourselves some work. And simple questions: do you like writing non-Linux drivers when you've got drivers that already work, or drivers that fail in the BIOS but work in Linux? It's just easier. And we talked to a lot of large outfits now that are kind of hanging on to this. If you've got an OS that works, put it in a BIOS, and then it works. Now, this is the we. At this time, as Los Alamos National Labs, got about 8,000 nodes worth of clusters that do this. We use Linux as the bootloader, since Linux can mount and use all the Linux file systems without the bugs that come with other bootloaders. And again, the question is, do you want to reset, write a whole new set of file systems in EFI environment or in forth? And the answer for me was always no. So all those custom entries apply to the file systems and network protocols and everything else. So it's an endless list, and it's growing. Although endless things can't grow. But Linux has the drivers, file systems, the command line interface you understand to make things get better when when things have gone south. So we use Linux as the BIOS and Linux as the bootloader at Lanolin, and on some machines we have at Sandia, because they're measured over a period of about 8 years, they've proven to be the most reliable and flexible and fastest way to boot the machine. I mean, it's fun to watch a PC iterate over 3 Ethernet interfaces with gPXE and spend about 5 minutes doing it in the amount of time that you can boot a 1,000-node cluster, because you have Linux in there and it actually does things in parallel, unlike most of these BIOSes that come with the machines. So in our experience, Linux as the BIOS and Linux as the bootloader always win. And again, partly it's the parallelism you get, but also the improved performance of the drivers. So here's actually a real life example that I had right before I gave this talk. So cache registers crashed and machines crashed. So I had a brand new oil PC, and I had a USB stick which I had just loaded, and I connect the stick to the oil PC and turn it on, and it says, oh, I can't boot the USB disk, and it says, okay. And the part I always like about that is that every time anything goes wrong on these open firmware machines, the first thing they tell me is that everything's okay. And I don't understand why, right? But they claim it's okay. So the interesting thing is, most of the time, the only time you really want to talk to the BIOS is when things have gone extremely wrong. A 1,000-node machine at Sandia, once all the nodes came up in that cluster and said, no keyboard, hit F1 to continue. So 20 people with the keyboard each fanned out to a couple dozen machines and had to plug in the keyboard, hit F1, and move on, right? So, it's not something you want to really deal with. And usually people don't really know or want to know how to deal with it, and they probably lost the manual. So in the case that things go wrong, I want a Linux prompt, right? I want a Linux shell. I want to talk to that. And I want a full set of BusyBox binaries while I'm at it. And people have done that. We're still doing it today. So the other interesting thing, and I've actually used this from time to time, I need to extend the BIOS for some reason. Doesn't really matter why, right? I need to extend what it can do. That's actually fairly straightforward, right? You insmod this or you mount that and you're done. So, you know, try and do that with EFI or open firmware. It's just simply not that easy. And with Linux, anything you're used to doing, a normal maintenance works when things have gone south and you need to get at the machine and fix it. So, you know, for our purposes in the HPC world, every time we've looked at this problem, the way we want to do this is put Linux in Flash. We've got the drivers and file systems. At Sandia, we had a company, well, okay, I'll just say it. It was Apple. They really, really wanted us to look at using Apple servers for clustering. And we said, that's fine, but we want InfiniBand. And the immediate issue was there were no EFI drivers for InfiniBand. Now, anyone who's seen InfiniBand knows that drivers for that are quite a huge piece of work. And you know, not having an InfiniBand driver for EFI, that is a showstopper for buying a server, is a real issue. If you have Linux in this, as your BIOS, it's not an issue at all. It just works. So the question is, I've got a dead PC, or you know, a board like this board sitting here. I'm not going to hold it up because I might break it. And the issue is, how do I get it ready to run Linux, right? It's a dead piece of iron. There's nothing set up. And I've got to discover, configure, and enable hardware. Well, before PCI, that was actually just a nightmare. I mean, anyone who remembers the dip switches on the boards knows what I'm talking about. You couldn't actually find out how anything was set. But post-PCI, the theory is you can configure all the hardware with nothing having been set up from firmware. So let's think about what boot firmware has to do. It's got to pick a boot device. It's got to do a little more configuration, if configure, whatever. It's got to find a boot file, the HCP, SF disk, whatever, mount it, validate it, and boot it. Every single one of those steps are easily done with Linux today. It all works fine. So, you know, again, Linux can be your bootloader. And hot plug was clearly coming, we felt, in '99, so that we really felt that we could just do a few changes to Linux and make it work as our BIOS and bootloader. And so our theory was in fall of '99 that this is Linux BIOS, okay? So, you know, there's where the kernel goes, and there's where the kernel is, up there in high memory. You do a mem copy and jump. Okay, done. That's the BIOS. Well, there was a little bit of a tiny problem, which I had lost track of because I hadn't done hardware for a few years when I got to this point, and that was synchronous DRAM. And even now, a lot of people, well, more people know than used to, but when you turn a machine on, the DRAM actually isn't functional. And it isn't functional for a very long time. And what you actually have to do is find out how to program it. And how do you do that? Well, you talk to the DRAM. But we just said that none of the hardware is functional. And actually, if you look at the very, very rough and extraordinarily simplified view of these platforms, you can see up there we've got the CPU, and then nowadays what we call the North Bridge. And there's the bus to the DRAM. But notice that DRAM module's got two little blue interfaces. And the blue interface on the right is a serial EEPROM. And to get to that, you go through the CPU, the North Bridge, the South Bridge, and the Super I/O over a two-wire bus called I2C that was developed by Philips for consumer audio applications. Hence, another way to interpret that is not terribly noise immune in all cases. And you ask the SEEPROM to tell you about the 30 parameters that relate to timing of this DRAM. Those parameters include loading. Nowadays, you tune the timing to 100 picosecond increments. You know, this is kind of a complicated problem. You don't have a stack. But you know, to do the most basic thing, you know, normally you've got to get a stack so you can have functions, except you don't have memory, so you don't have a stack. You've got to configure PCI. You've got to do I/O over I2C. Thank God it's not USB, right? We'd never get this done. You've got to read those 30 parameters. You've got to do some computation in the 8 or so registers you've got available, and you know, do some minimal turn on and set up DRAM and code Linux. So we did all this. We did all this in a couple of months. We relearned a lot of things that people had forgotten about hardware because BIOSes have been doing it so long, which was one of the most interesting thing about this project is actually essentially re-educating people about what happens in hardware. And we were actually surprised to find out how many things people, including ourselves, had forgotten. So we called Linux, and it was great. got serial I/O from Linux, and it didn't work at all once we started to do I/O. And what we found then is, well, Linux has a little trick it does with PCI devices. If they are not turned on, they are soon to have been disabled. So we thought this would kind of work because the SGI Visual Workstation, but we were wrong. So we had to do a little bit more. And it gets a little more complicated at this point. So we do display init. You pick the PCI configuration method. You do things with the super I/O because super IOs still aren't really enumerable or discoverable in a straightforward manner. Then you enumerate PCI, turn on the frame buffer if you want to, enable PCI, blah, blah, blah. At some point you've got DRAM up. So notice we had to set up all PCI because of just this interpretation that Linux applies, which is very reasonable, right? Until we started doing this, Linux had never hit an unconfigured platform, literally. And I talked to the Linux guys at the time, and they said, we're pretty sure we can configure an unconfigured PCI bus, but why don't you try it and let us know? And the answer was, no, you can't. So the next good fun was with SMP. And the first theory there was, yeah, BIOS has been doing it, but maybe it's not doing it as well as Linux might like. So we had a summer student basically go from the Intel spec for SMP bring up and write C code, which we plugged into Linux to do the SMP bring up. So that was kind of interesting. It was the first open source C-based sort of bring up for SMPs. There is an issue, though. The Intel Pentiums at the time used a voting algorithm at PowerOn to pick which one of them got to run. The K7s didn't work that way. The K7s all came up running. It was your job to stop them in software. So this idea that you would boot all the way to Linux and then figure out which guys to turn on is kind of flat out, right? You can't do that because they're all on. And in the BIOS, they're all busy interfering with each other as they try and turn on DRAM. So we actually had to push that SMP startup back down into Coreboot. And that actually turned out to be a good thing. A very smart guy at AMD, Yinghai Liu, has actually made the memory init in the K8 parallel. So the K8, there's the North Bridge in every CPU, and he's done some very interesting stuff. And basically, we bring the machines up SMP. And every once in a while, I'll run into somebody who says, boy, wouldn't it be great if the BIOS were SMP safe? And we say, yes, it is great, because we do it. And you've got 128 gigabytes in a machine, and you do a memset, it's nice to have 8 CPUs doing that rather than 1. It noticeably chops down the boot time. So, our initial model with this was Linux is going to do everything, right? We're going to do a mem copy and jump to the start of the kernel, and we're done. And part of that was there used to be a comment in Linux, we don't need no stinking BIOS, which I think is or should be gone because it does now. Linux has evolved, we've all evolved and gotten older. And Linux really does actually need that BIOS there. It really depends on it more than ever for services. But at the time, it worked pretty well. And part of this was, well, what can Linux not do? And then we got back to, well, let's let Linux do a lot of it, and certainly a lot more than DOS does. So where we are today, Coreboot proper is a simple payload loader, which is hence part of the reason we changed the name, because it isn't dependent or doesn't require Linux kernel in there anymore. And then we've got all these targets. We've put Plan 9 kernel and Plan 9 loader in firmware, in the flash part, and booted that directly. There's a really neat bootloader project called Philo. Philo can boot your machine whether there's a BIOS in it or not. So it's got drivers. Notice, though, we find ourselves writing drivers again for bootloaders because people don't always want Linux in there. Sometimes you've only got a 1/4 megabyte of flash, and in these days, a 1/4 megabyte is far too little room for even a compressed kernel. Memtest 86 is a pretty popular payload. It's a good way to really wring your memory programming out. And there really are still a lot of cases where there's a Linux kernel in flash or Etherboot. And we've got a demo of almost half of those configurations up here today. So the key thing is we finally own a platform, right? Anything you buy today that looks like a PC, a lot of things happen. You don't know what most of them are. A lot of people don't know this, but a lot of the BIOS is still actually operational and can run once you've booted your OS. That should actually scare people who really care about security, right? There's a binary thing in there. You don't know where it came from, who wrote it, or what it does, and it's running while you're running. And by the way, that binary thing is happily able to read any piece of memory, any block on disk, and do anything it wants with the network. So, I I actually started kind of pushing this message around inside DOE, and people are starting to worry about what that really means. The other thing is, you know, I try and tell people this all the time. There's a global community of people who support this code. So when a company comes to me and says, "Whoa, boy, we don't know how to support a BIOS," and that's why we get our huge ball of assembly code from Phoenix and hack on it, I say, well, you know, you guys use Linux, don't you? You've obviously come to terms with the fact that there's a global community of people who support that. Same thing applies to Coreboot. Same thing as that applies to any open source project. So we actually have one or two vendors pretty heavily engaged. AMD has 2 guys who do this stuff full time. So we get support from them. VIA is contributing code now for their newer processors. So we really have sort of this growing collection of people, some at vendors, some at mainboard vendors, and then of course the usual volunteers like us, people who make money from it in some cases. But you really want complete control, and you want it for purposes of speedy booting, security, and control of the platform. The other thing that has changed in Coreboot, remember I probably hinted I don't much like ACPI. You can't get along nowadays without ACPI. So Stefan has been developing open source implementations of ACPI and system management interrupt type support code. So that is about all I want to talk about because we have a lot of actually material to cover. I thought I would do a demo of a Coreboot based cluster. We built this thing 7 years ago. And let me quick switch to demo 1. This thing has actually been through the wars. This has been involved in more airport baggage incidents than I can name. It's got a frequent flyer number. That's not working. Demo 1, right? Oh, well, that's okay.
Hold on.
Oh, okay, they're getting it set up. Basically, this has a node at the top of the disk and then 3 nodes that are Coreboot nodes that quickly boot Linux. And I'll be able to show you how quickly in a minute. Well, while they're setting that up, I'll show you. Okay. This is running software developed by Eric Hendricks, who now works at Google Seattle, called bproc. And you can kind of see we've got 2 nodes up. And it actually won't, oh, I'm sorry. It actually won't, well, I'm going to have to switch it and switch it back. I just reset node 0, okay? And it'll actually be a second before it realizes I've just blown that node away. And I'll mention while I'm doing this that this is the identical, oh, yeah. So node 0 is down, node 0 is booting. Node 0 is up. So this is actually the same software we run on the 1,000 node and 1,500 node and 2,000 node cluster at Lanel and at other places. And observation on the 1,000 node when we first built it is it boot all 1,000 nodes from power on in 2.5 minutes, while the nodes with conventional BIOS were busy trying to tell you that they might be coming up. So what that looks like from the sort of point of view of the cluster node itself, this is the serial bus. And let's see if this will go. So this is kind of, this is what our cluster nodes at Lanel look like when they booted, okay? And you can see the longest step is just getting that kernel in, but the thing is pretty much up at this point. So that's booting the kind of cluster nodes we build at Lanel. The thing that would typically take a little longer is if you had a MirrorNet in there, because MirrorNet discovery and setup takes a little bit of time. But anyway, that's kind of how we do these things. And where am I on time? I'll do one. Should I do the build demo real quick? Okay. So I'll do one more thing because we do need to, we have a lot of stuff to do. This is kind of a build, a build sort of showing you what it likes to build this thing. So I'm going to build it for QEMU. And I'm taking a chance here because of the dark angel of demos. But anyway, Russ is going to chuckle because Plan 9 still builds faster. But, so I just, oh, and I got an error. Dark angel, oh, that's because I've been hacking on it and I put in a note to myself. Anyway, normally that would be done, and then I'd go upstairs and I would run it. And, that's a splash screen because everybody's got to have a splash screen. So, sort of build and boot cycles with this thing are pretty short, unless you purposely inserted a comment to make it not build. Anyway, so that's sort of the HPC perspective. There's been a lot of use of this in HPC. There was a company that sold only Coreboot because it lowered their maintenance costs. They'd give you a price discount if you didn't order Phoenix or AMI BIOS on your cluster nodes. because they discovered that it was cheaper to maintain and support them that way. Anyway, I'm going to move on. Peter's going to talk next. Do I disconnect from the laptop and you go in? And by the way, we are here for a while if you have questions and you want to talk to us about things. And I'm actually going to pass around a version of the mini cluster for you to look at.
Yes. All right.
When you get that, be sure to hold it from the bottom.
Right. Please grab it on the base. Yes. So short outline. Who am I? Coreboot competition overview, motivation, a bit of technical detail about Coreboot. Some of this has been covered by Ron already. Payloads, important part of the Coreboot ecosystem. Auxiliary tools that we've encountered we need when working on Coreboot. Demo time, some security, comments, conclusion, and thanks and links. I work in Sweden. I'm self-employed consultant. I do software hardware security, prefer open source embedded stuff. I found Coreboot back in 2001 when I was working on developing a set-top box for a broadband provider in Sweden. We didn't end up using LinuxBIOS as it was called at the time, unfortunately, but I stuck with the project, and in 2006 there was a developer meeting in Hamburg where I met Stefan and Ron and a lot of other cool guys and got involved. These days I do work on FlashROM, MSR tool, Philo, a bit of K8 in the version 3 bring up, support, and some marketing. So Coreboot is a BIOS replacement, as we heard. The BIOS really does only two things today. It does hardware in it, and then it starts up the operating system and provides these interrupt services for really old operating systems. But all other operating systems, they have their own drivers. ACPI part, as Ron mentioned, is still important, but not something we can't do. So why do we want to change this? Why Coreboot? The BIOS used to be a library, always called by the operating system, but some stuff happened and laptops came along. System management mode was introduced to handle the suspend or the hibernate. How many of you know what system management mode is? Hand up. Okay, cool. For those who don't, then maybe a short recap here. It's a new execution mode in the 386 mobile CPUs. Basically, when system management mode enters, or you trigger system management mode, execution comes to a complete stop. The CPU switches to a predefined state, sort of an isolated state, runs this configured handler that you've set up. And this can be triggered by a new electrical signal, of course, so that when you close the lid, code runs and saves up your state. Can also be triggered by software, though. So from RAM access or I/O access. And this is used quite a lot. You'd be surprised. After APM came ACPI from our friends at Hewlett-Packard, Intel, Microsoft, Phoenix Technologies, and Toshiba. The version 3 document that I have is 600 odd pages, and inside is, among other things, a virtual machine specified. It has its own bytecode, and it runs stuff in the BIOS, so outside the operating system. Really outside the operating system? Yeah, at first they did that, but this virtual machine in the BIOS was such a performance hit. I've seen the number 5% performance lost because of this, that they decided to move the virtual machine into the operating system. And in Linux, this happened around 2001. I've seen the number 90,000 lines of code to do this. The fun part is that it still runs completely outside the operating system security model, because that's the way it's designed to work, so that's the only way it can work. Kind of scary. And what are the others doing? The BIOS started out in '78 as a tape drive I/O abstraction layer, and in 2008 it's still there abstracting hardware, but it also does a lot of other things. 100+ function calls, mostly real mode code. I listened to a vendor talk. They told me how they have a really good code base that's it's 4,300 assembly files, but it's modular, so it's really easy to work with. I don't know, maybe yeah, I don't know. EFI, pretty much an operating system of its own. It has networking drivers, it has various services. It's open, they claim, because you can get the specifications and you can write plugins or applications in this in this operating system, sorry. But you don't get to see what's going on inside EFI. If you do get access to that code, you have to sign a lot of documents saying or promising that you will never tell anyone what's really happening. Tiano Core, the Intel EFI implementation, the code base there is about half a gigabyte, so 250 megabytes. Compare Linux kernel, which is 50 megabytes. There's a lot of other stuff in this area. Grub and Lilo are bootloaders loading kernel from disk. We don't really work with them. We have other options. I'll tell you in a minute. Redboot is sort of similar to EFI. It's based on the ECOS embedded operating system. It's really common for mostly smaller systems, whereas, as you heard, Coreboot has a sort of a focus on large N, but it works really well on small systems as well, as we'll see in the demo. Uboot is another bootloader popular with other architectures, maybe Power, ARM, MIPS, etc. So BIOS replacement, how do we do this? Coreboot only does the first part, the hardware in it, as Ron told you. And we have a concept of a payload, a separate program that takes over, starts the operating system, or runs your application, or does whatever you want your system to do. Coreboot and the payload goes into the flash chip. And we have a whole bunch of them. Of course, we have bootloaders, Philo, boots from local storage, CD-ROM hard drives. Etherboot, GPXE, boots from network storage. CBIOS is an open source BIOS implementation. So you can boot legacy systems, BSD, Mac OS X recently, Stefan doing some work. DOS works fine, even Windows. There's open firmware if you like that. If you want the OK message all the time. You can use Linux as a bootloader also, as Ron was talking about. Grub2 will work, hopefully, someday with Coreboot. There's been a lot of work put into it, but it's not yet in the official Grub2 code. It's in a separate repo. We also have utilities that can run as payloads. Memtest86. Coreinfo is a utility we developed. Linux, again, if you want that bash prompt or ash prompt in your BIOS, so to say, then put a Linux kernel there and init ramfs, and you're done. But what I think is really cool also is the applications. You can make applications into payloads. So we ported Tint, which is a nice game. I'll show you in a bit. Bayou is worth a special mention also because Coreboot can only start one payload, and the payload can never return to Coreboot. So maybe you want a couple of these, and then you need Bayou. Bayou is combines several payloads into one, and you can either get a menu interface where you choose which one you want to start interactively, or you can script it. So Tint and Bayou and Coreinfo, they're all built using libpayload, which is a simple, small C library that we put together and a compiler wrapper. So instead of running GCC on your C app, you just run LP GCC, and out comes a payload binary. This, of course, only works if your application doesn't need operating system services. But if you have a really simple app, this is a nice way to get it into a payload. And there's even curses, a small curses implementation in this package. So some of the auxiliary tools, we have BuildROM. Good because Coreboot and payloads and kernel versions and configuration, and there's a lot of stuff to keep track of here. BuildROM is excellent because you just choose, I have this main board, I have this big flash chip, I want this version of Coreboot, and I want this payload, go. And BuildROM does everything you need, and out comes this ROM file that you can put into your flash chip. Make elf image needed because the Linux kernel can't be started as a payload just directly. It needs this small piece of glue. So that's what we use so far. NVRAM tool flips bits in NVRAM. It's really neat because we have an options file which describes the NVRAM layout, and you can use this also with factory BIOSes. SuperIO tool, Intel tool, MSR tool are all good for looking at the state, the registers in SuperIO chips, and the Intel chipsets, and MSR tool is a generic tool for any chip with an MSR. So there's also FlashROM, which deserves a special mention. It does BIOS upgrades for BSD, Linux, Solaris, and pretty soon Mac OS X too. You can do cross-flashing, a normal vendor BIOS tool. So, okay, normally you have to create this boot floppy drive, boot floppy disk, and put it into your system and start up and run this old DOS thingy. It will check, OK, you're running on this main board. You're trying to flash this image. They don't seem to match. I'm not going to let you do this because you might wreck your board. And sometimes you want to do that. And you maybe not always want to flash the image from the vendor. So FlashROM will check if you're doing this, and it will warn you, will let you know that this doesn't seem to be appropriate for this mainboard, but go ahead if you want to. FlashROM at the moment supports more than 100 flash chips, 66 chipsets last time I looked, and 20-something mainboards, which can actually be even more because mainboard vendors often tend to just use a reference design, make a few small changes that are unique to them, and the stuff that matters for FlashROM can be the same across a whole bunch of mainboards. And finally, push-pin flash. If you're starting to do this a bit and you want to swap flash chips around a bit, this is a great invention that I wish I could take credit for. So you take this corkboard tacks and cut off the metal pin, glue it on there, and you have a nice knob or a handle that you can move them around with. Plus, you can color code. So demo time. I'm going to show you an Alex board. This is a Geode LX CPU board, 500 megahertz CPU. It's running Coreboot version 3, and it's running Linux from the flash chip. On the screen, you can see the serial console. And let's see how it works. So we see Coreboot starting up. OK, the kernel is starting up. And now we have some init scripts that are running. That takes a second or two. You can trim this down, of course. But it's still pretty neat. And we're done. So that's the first demo, and let me switch over to demo number 2. So we should get a signal here anytime soon. Yeah, here we go. OK, I was told that this might not come across correctly for the video conference, but I hope you can see it anyway. This is showing the BIOS payload, where I've built in 3 different payloads. I built in the core info system information payload. Looks like this. We get some information about the CPU and about which PCI devices we have and the config space. We have NVRAM dump, and we can also look at some Coreboot information. We see that this is a PC Engine's Alex 1C board running Coreboot version 2. I built this in September. So we're done with that. We see that everything looks good. We go to play Tint. That was good work. So let's have some fun with that. And when we've won this game, we start Philo. And yeah, again, the init scripts. Oh. Yeah. So there we go. Pretty slick, I think. Some attack ideas. You may have heard about Jake Applebaum's Cold Boot paper, which describes how RAM doesn't really lose all the data after you power off immediately. So data can remain in RAM for up to 30 seconds or maybe even longer, depending on the RAM chip, and if you cool it, of course. With Coreboot, if you could inject Coreboot into the system, after a reset, you can just dump out all the data immediately. Because we control everything that's going on after RAM init and RAM init itself. Once RAM init is done, let's read out what's in there. TPM emulation, because we can trap hardware access. You could be running on a system and your operating system or your app is trying to do some kind of TPM verification. This is trapped by the SMI handler in system management mode. Off it goes on the network to that other box in the corner from some big fruit company. And when the response comes back, hey, you're running on this fruit box, so let's go ahead and run your app. SMM rootkits, of course, you can intercept whatever, move hard drives over to another system over the network, or do some fun stuff with the CPU fans by changing the speed of the revolutions. You can play sound, or you can force a user to play Tint until they win it, and only then do they get to boot. So defense is pretty much the other way around, just the mirror image. You can make sure that RAM is scrubbed whenever the machine is started, before the machine is shut down. You can do it in case someone opens the computer case, intrusion detection. You can filter ACPI stuff, what ACPI is allowed to do and not. You can implement some simple ACLs. This device with that and that serial number has to be connected before boot is allowed. And virtualization means that you could just make sure all your data is encrypted, so that if anyone comes along and asking questions, I don't know, have a look at the machine. I don't know. Flash lock bits, flash chips, and chipsets can be set up so that flash writes aren't enabled. It's impossible to enable them again without resetting the system. And if you do this, you're pretty safe. And you can, of course, also hide flash contents so that anyone who's trying to access the contents of the flash chip, they get what you hand them. And no offline analysis is possible. So what's the conclusion here? There's a lot of good stuff. We have a quick startup time, as you see. We have open source code. Coreboot is GPL. libpayload is BSD, so that it can be used for all sorts of applications. Open source means auditability, of course, which is nice. It's written in C as opposed to that vendor with thousands and thousands of assembly files. We have one source tree, whereas most commercial vendors, they take pride in having one source tree per main board. It's not a bug, it's a feature, because you have this BIOS out in the field and you want to make some small change, but you don't want to include all the new stuff that was done on XYZ desktop mainboards. So you just take the old tree, make this small change, and release a new version. Of course, that's possible to do with some clever version control as well, but I don't know. They might not have caught on to that. So the one source tree, it's easy to reuse code. It's easy to extend. Also, C is, it's so much nicer to work with in many ways. We do need more testing, and for desktop users, I think we have really only one mainboard that's perfect so far. But many more boards aren't very far behind. They only lack small things that no one just has stepped up to fix. So ACPI is one of the problem areas, because vendor BIOSes, they have these ACPI blobs, and they are needed for suspend and resume, for example, and we can't use them because they're code and they're the property of the BIOS vendor. But we're getting some help writing good ACPI code of our own, fortunately. So there's a lot of fun stuff going on. Please come talk to us. I want to say thanks to David for inviting us here, and this is just a webography if there are if there's something you want to check out. So I guess Stefan is up. Yep.
So hi, my name is Stefan Reinauer. I work for Core Systems, the company I founded in 2005, mainly working on Coreboot support and trying to get in contact with vendors and supporting other commercial applications of Coreboot. Will be a second. Well, where's the VGA? Here. So I used to work for SUSE a while back, doing the initial AMD 64 port of LinuxBIOS back then. And I switched over to do some embedded work after that, writing software for the ICE trains in Germany. But since that was very high safety, high security kind of thing, I thought I'd love to go open source. So I switched completely to Coreboot. And by now, I hope we're up.
Yeah,
It's coming. Great. Okay. Oh. Does it work?
We're not getting a signal in the back.
Oh, I'm sorry. Oh, it's doing this.
So, any questions so far for Ron or Peter?
Okay, thank you. So the topic I'm talking about is quality assurance and testing, because I figured if we have something like 100 boards in our tree, testing of those targets becomes more and more important. And this work was actually done 2 years ago and was funded by Google. Thank you very much for that. So why do we need quality assurance? I guess quality assurance is very important for Google as well, so you guys might know even better than I. We have an asynchronous development model. We have something like 100 different mainboards in our tree these days. And obviously, since we're an open source project, no developer can test all these supported systems before making a check-in. So this is crying for breakage in the tree, right? And so the system is also, we do code reviews, but the system is also quite complex, especially when it comes to RAM controllers. So you can't find all regressions through code reviews only. And like there's a butterfly effect. You change one line of code in the RAM init and a whole number of mainboards just breaks. We've been having this a couple of years back when one guy was checking in some stuff overnight at 3 o'clock, and the next morning we all got to work, like exactly one mainboard was still working. So we thought about trying to improve on that a little bit, and this is what we came up with. So we're doing system tests, and I think testing is quite essential in any engineered product, anything where especially several people work on and you want to use it in the end. And we want to check whether the software actually does what it's supposed to do, what it's expected to do. But also testing is considered a burden for developers, for all developers. I don't know. It forces to have a clear concept of software development, so it's not actually a burden. But we decided to go with the first step and do system tests that look at the whole system at once, as opposed to doing component testing. And we came up with we need to test against formal requirements, so we write the stuff down that we want to test. And we do black box testing. So that's the simplest thing to do. We just put a system there and observe what it's doing. And if it does the right thing, we're fine. So we wanted to automate all this stuff because, as I said before, no developer can test all these systems manually, look whether something broke. And so to automate, we needed to enforce formal test conditions because we wanted reproducible tests. And we also wanted to do regression testing, so new commits don't break old stuff. And yeah, we kind of require instant test results for single revisions. So we immediately, when somebody checks in something in the tree, we want like to see the culprit, see what's going wrong, so we can fix it in time. And of course, we are trying to reduce the time developers would have to put into it. So yeah, this was like in 2006 when we started. We kind of had an automatic build system that was running on each check-in. and reports were generated. The URL is actually wrong. Back then it was snapshots.linuxbios.org. By now it's qa.coreboot.org. And we used to ask people before they check in something, please manually test your changes. Please run our auto build system. But guess what? Nobody actually did that. So yeah, our automated system we had back then only checked configuration and compilation. So this was kind of the vendor BIOS. It compiles, let's ship it approach. And we really don't want to do that. So this was the old stuff we've been having. You see the logs. And so then we came up, thought, how do we do tests? So we first built the images. That's the blue box on the top. On every check-in. Then we generate check-in reports, build reports. Then we pass those images into our test system. We generate test reports, and those tested firmware images become good firmware images. So we offer them for people to download if they succeeded on a given system. Yeah, every revision gets tested, and single developers can also put in their intermediate versions of trees. So if they don't have a hardware at hand, they can sit anywhere in the world, submit their BIOS image, say, please test this code base on a couple of nodes. So that would work fine. And they would get back an extensive test report with timestamps and everything of the boot up. And yeah. So in the beginning, when we made this concept, we actually thought, well, if we do this test system, we should really block commits that would break the tree. But imagine that in an open source project, and we'd been like, back then when we initially did that, we had a pretty slow machine, and compiling all targets, like back then 50 main boards, would take almost an hour. By now we have a faster machine, which is a dual Opteron, and it's like it compiles 100 main boards in 20 minutes. So, but still 20 minutes, so you can block the repository for 20 minutes on every check-in. And so the compilation and tests are actually running asynchronously. And if you have like a dozen check-ins every day or even more, blocking the repository for several hours, that's not an option. We can't do that. Also because the test environment is supposed to help and not enforce people and not block people. But we came up with a solution that it would at least help if we try to write blame mails. So if someone actually breaks the tree, we would post to the mailing list and say, look at this guy's code, he actually messed up. And if he doesn't fix it, please someone back it out again. That's what we're still using today. It works pretty well, actually. So here's how our test setup works. We have a central automatic build system, that's the blue box on the right, which compiles all the images and hands them out. Then on the side we have something we call the test server, which is a little box that controls the actual main board we want to test. Then we have the system under test, the SUT, that's basically the main board. And we talk to the main board with as simple interfaces as possible. So we have the serial console, we have Ethernet, and we control the power of the machine. There's a number of other things that we could potentially do, but we're going for these things for now. And we really needed one thing for that. That's a reliable firmware update. So you could not log into the machine and just flash a BIOS and it would not come up, so you'd block the test system for another couple of days until someone manually fixes it. So, yeah, the hardware is an issue if you do BIOS testing. So we had to create reproducible results by actually one way of doing that. One factor is you have to unify the start conditions. So all components are actually controlled via USB or Ethernet, and we use power switches to really power off the systems. so they come from a cold start and don't have leftovers from former BIOS versions in there. And also, the system is supposed to scale, so a single test supervision server, which is actually just a box like this big, it can control many different systems because everything's controlled via USB. So you just add a USB hub to it, and it's all low traffic. You can, I don't know, maybe put 16 main boards to one such box. For the remote BIOS updates, there was, back when we started doing this, there was one solution that was pretty neat, actually. That's a Promise memory controller. Sorry. Yeah, it used to be, I don't know how much they are now, but back then they used to be like $2,000 per device, and we planned on like at least supporting 100 mainboards, so that's 200K right there. That's pretty much way beyond our scope of setting up such a test system. So we came up with alternatives, and I started with my crude fingers building small custom hardware controlling the power of the system and attaching this to a BIOS savior. So the BIOS savior would actually, that plugs, it has two BIOS chips in there, one on top and one in the bottom, which you can see. And so we controlled that BIOS savior via the small custom hardware, and we could also soft power on and power off the machine. So with this thing, we could also do in-system firmware updates, so we could test our flash ROM utility with that. But time has passed, and then Artec Group came along, a company in Estonia producing this very nice device, which is also a memory controller, a memory emulator. It has the flash chip, and it contains an FPGA talking to an LPC bus or to a firmware hub device. And Peter Stuge actually built these very nice adapters, so I've been using them a lot. And with this thing, you can use during development or testing, you can just plug the device on the one end to a USB connection, on the other end right into a BIOS socket, and you can automatically update your systems at any time. And the nice thing is, like, it's kind of hard to produce hardware and sell them if you're a small company. So this is off-the-shelf hardware. We can just grab it and give it to people. Pretty good. For power control, we initially used, we're looking for a device that would work in the US and in the EU, so a lot more people could actually use that. I found the IPS 400 remote power switch, which you see on the picture as well. But that's quite expensive, so we were looking for alternatives here. It's like a couple $100, I don't know, 19-inch component. So we found X10, and we found some remote power strips, which you get for like $10. And of course, we can still do the soft power control. So we attach a little switch, electronic switch, to like the reset line and to the soft power off switch of the machine, ATX power off, and we control it like that. So how do we distribute our images? There's the repository on the top, which is one of the central build components. There's the auto build system, and on the same machine there's living the software to manage the testing, to process the results that get sent back. And there's also distributed components, like the systems under test and the test supervision servers, which you see in the bottom. And they're all connected over the internet. So we try to keep this as simple as possible because we knew maybe we won't have internet access to people's server rooms, whatever. So all that is needed is an outgoing HTTP connection to coreboot.org. And this is what our test infrastructure looks like. So the Coreboot images are generated by our AutoBuild tool, which is part of the source tree. I actually even use it for development because it's really simple to use. And you can either build a single image or images for all mainboards. And The centralized part of the system actually can be looked at qa.coreboot.org. I think the test system is not really running very well at the moment because I disconnected the last node a couple of weeks ago. As soon as I come back, I'll put some more systems in there. And there you actually get detailed information on each test run. So that's basically what it looks like. You see like the number of failed tests, the number of succeeded tests, number of failed builds, and it tells you whether it's newly broken or if it has been broken for a while. So these test reports can be used for monitoring the progress of Coreboot. So you see configuration errors, build errors, test errors, but they can also be used for debugging, which is actually a pretty interesting thing. So the serial logs, I mentioned them before, include timestamps. So if we have bottlenecks, if we have suddenly like need 5 seconds to boot instead of 2, we can check the log and see, okay, there's something weird going on there, and we gotta check that. And of course, there's the test results. So attached to a help system. So with each test result, if a test fails, you get a number of suggestions what might be wrong. So if you can't copy stuff to RAM, it will tell you to check the RAM controller configuration. If interrupts are not working, it will find that out and tell you, please check your interrupt setup. And it tells you probably this might be an ACPI problem, or it might be a problem with the MP table or IRQ table. Those test reports are all XML files, so it's easy to post-process them. And I wrote a little theming around that, so they integrate nicely into the Coreboot website or any other website. And yeah, I already mentioned that too. We now have known working BIOS images, so nobody has to create expensive bricks out of their hardware. The image deployment, I think I'll go over this real quick. So the payload, we have a payload repository which actually allows it to build different kinds of images with different payloads. So we could build images with the kernel or with, for example, a BIOS emulation or with an EFI interface, whatever. And so all this stuff in the backend is XML also. And so yes, that's about it. The stuff that happens on site, you need one supervision server per site, or maybe more if you want to test a lot of mainboards. And the good thing is all these systems under test, they're all powered on only during tests. So if somebody checks in something new, like several mainboards suddenly power on, will run the tests, power off again, and the test will be submitted back to the test server running at Coreboot.org. So I've been like having this in my office for a while because it's really not running very often, like several times a day. So in the middle of the night at 3 o'clock, it suddenly powers on, runs a couple of tests, switches off again, and works fine. And yeah, one thing to make it simple is that the test supervision server, so the thing on site is actually polling for new Coreboot revisions. So you don't have to open the firewall to actually let something outside go in there. And it's all written in shell scripts and so easy to maintain. That's what it looks like. A small box, low power consumption, no moving parts. And when you run tests, the tests are always checked out together with the actual Coreboot release. So you can add a new component and also add the test with that component to keep testing up to date. The test framework, it's actually written in Deja GNU, which is kind of nice, but it's also kind of old. Back then, a couple of months later, I think, I found out about the nice Google framework. I will look into using that for another release. But so far, Deja GNU is actually working pretty good. And we use small helper programs that we plug into it for firmware updates, power control, serial console. And we have a, well, not so comprehensive amount of 26 tests in the test system at the moment, but we're improving on that. So we test boot up, machine state, is everything set up correctly, and is the machine actually usable? And we also have an interface to Intel's Linux-ready firmware developer kit. So we can plug in those like ACPI tests and different machine tests that Intel invented to make our stuff better. Together with that, we started writing IEEE compliant test documentation because some of our customers actually want that. So that's like the interesting stuff. Where is this all going? Of course, we want to test all main boards in the tree. Maybe we will not reach that state, but at least improve on the number of main boards. As I said, it's really right as we speak at 0, so it will increase pretty well as soon as I return. And we also want better integration with the upcoming Coreboot version 3. We want to test VGA initialization on our nodes, on some of the nodes where VGA actually plays a role. And one interesting topic is also, of course, code coverage testing. So we want to see which code is actually run and which code is actually not run. And we don't do that only for the stuff that is running out of RAM, but we also want to do that for the code that actually initializes the RAM. So we really get a better understanding of the quality of our code there. At this point, again, I really want to thank Google for their support for funding development of this test system, and of course also for funding our Summer of Code students this year and last year. Thank you, guys.
Before we move on to questions, I'd like to do one real quick demo here. It's building payload.
He's going to be plugging into that guy. Here. I always wanted this anyway.
On.
He's plugging.
Okay, so I want to demonstrate real fast how easy it is to, well, get your firmware on. So I have here a checked out copy of BuildROM. If you just Google for BuildROM, you'll get straight to the source, and you can just check it out through SVN. We use make menu config. We hijack the Linux kernel build system. Do our Coreboot configuration. Here I'm going to use version 3. I'm going to choose my platform. I had it set up for PC Engine's Alex 1.c. And of course, there are a couple more options. You know, we got some reference platforms. We got some other mainboards, etc. And for my payload, I'm going to use core info, which you saw earlier. It's a utility from AMD that dumps a whole bunch of cool information about your machine. Going to make it. Oh, whoops. Make. In my other window here, I'm going to actually configure Coreboot itself rather than the payload. Oh, and I should probably full screen this. I'm sorry about that. Don't need to worry about most of this. You know, it's kind of like Linux kernel configuration. You go through, you kind of select the options for your hardware. Let's see, debugging. Oops. All this good stuff. I'm not going to worry about power management. I'm going to select core info as my payload here. So let's just pretend I spent some time thinking about that. Save it. And let's see here. OK, my payload here was built.
Those are two different ways to build it raw, right?
Yeah, there are several ways to do it. This is the easiest, in my opinion. So I'm just going to hit make right there. No funky, you know, Microsoft compilers, no ancient tools. This is all the standard GNU toolkit. And I'm done. My firmware image is right here in build BIOS. And so right here, I'm going to demo it running in QEMU. Actually, I'm going to demo something that you can look up on your own. So Coreboot QEMU. Hit the first link. I should have hit I'm feeling lucky. And Dark Angel of Demos is breathing down my neck. I hope I am feeling lucky. And we have ready-made QEMU images here. You can get started right away. And we tell you how to download and configure QEMU. And I've done that here. So here we go. And we're up. Any questions? Oh. Thank you all for coming then.
Thank you.